Hello, I'm Lenora Clark, Director of Autonomous Driving and Safety Technology. My team and I have put together a series of short webinars to educate you on various materials used in the build of electronic hardware that supports advanced safety systems. Throughout the series, we'll look at designs from the perspective of printed circuit board, assembly materials, and materials used to enhance some semiconductor packages and IC substrate designs. I invite you to think of the parts of these builds and how they affect the whole. As we travel this web series together, I'll simply be your tour guide. I'll show you some cool things from a materials perspective, but ultimately you know your designs. You understand their challenges and the overall performance expectations. You'll choose the appropriate materials to deliver success in your product. But to help you achieve this next level of autonomy, I'll supply you with valuable information and focus on three areas: form factor, performance, and reliability. Today we will explore radar sensors. They're actually one of the main systems among advanced safety offerings. As a society, we're inundated with transportation choices. Your location and lifestyle likely dictate your preferred method. The automotive industry is experiencing a time of dramatic change, and it's partially to define its presence within the consumer choice and partially to establish a sustainable future for this market. Safer vehicles that travel more efficiently will affect us socially, economically, and environmentally. The simplicity of making a vehicle safer actually has pronounced positive impacts on us in so many other aspects of our lives. So what does the road to a safer vehicle look like? As we travel this path to full autonomy, the car form and function will completely change as we know it. The Society of Automotive Engineers describes this in levels. Level 0, the driver makes all the decisions. In level 2 and 3, the car informs the driver of hazards and in some cases may interfere with the car for a better outcome. Finally, level 5, the vehicle completely drives itself. In new car offerings today, in the new introductions today, they're delivering level 2 and level 3. And a great example of this is lane departure warning and collision avoidance. So if you're an ADAS engineer, you understand how these things work. But do you understand how material properties affect the system? Let's take a look at how these systems work and the hardware associated to their function. The technology used for advanced safety systems such as automatic emergency braking, blind spot detection, and collision warning are forward-facing cameras and radar sensors. Today we'll dive into the design and the function of the 77 GHz radar sensor. I'll explain why automotive moved from 24 to 77 GHz, and we'll discuss the effects that has on material choice for proper performance. Radar is an acronym for radio detection and ranging. It utilizes a military combat technology. Basically, an antenna sends out a signal and then receives that signal back. In our case, the antenna to create this function is a very specific circuit design. When the signal is sent out and hits an object, then is returned, it gives us information about the distance and the speed of the surrounding objects. In automotive, the first advanced safety system offered was blind spot detection. It was introduced by Volvo as a camera in the side mirror, and it warned the driver of objects in the blind spot. This feature was later offered by other car makers using radar sensors. Again, the system informs the driver through lights or beeps that something's in the blind spot, and it was originally designed to be used at 24 GHz. But due to markets using that frequency and the limitation of the technology, the automotive industry has moved to 77 GHz. 77 GHz offers better resolution. And the best way I can describe this is through a story that was told to me. When a system functioning at 24 GHz approached a mountain that had a tunnel in it, it actually came to a complete stop. The system could not resolve that there was a hole in the mountain it could transfer through. When we increase to 77 GHz, the resolution becomes greater. the system is able to distinguish different things around the car, understand what's around the vehicle, as well as distinguish the fact that there's a hole it can transfer through in the mountain. So the automotive radar sensor is a printed circuit board assembly. It contains an antenna on one side with very specific components that send and receive the signal, and the opposite side is a more traditional circuit. To support the function of the antenna, the industry uses a very specific high-frequency, low-loss substrate material. And actually, the vast majority of the industry is using PTFE, or polytetrafluoroethylene. It has excellent electrical and mechanical stability. And we describe this through dissipation factor. So the lower the dissipation factor, the less signal loss. For a conventional FR4 substrate material, the dissipation factor is 0.02. For the PTFE substrate, the dissipation factor is 0.004. So less information is lost. The shape of the antenna is also critical to its function. We understand that as frequencies increase, the tolerances become more critical. This simply means that the shape of the antenna plays a more predominant role in its function. So for a radio frequency circuit, insertion loss is basically the sum of multiple components. You can have loss due to the dielectric, which is the substrate material, or you can have loss due to the conductor. And this could be from the height or width of the trace, the antenna in our case, or the surface finish that's chosen. In this chart, we're looking at skin depth versus frequency. As frequency increases on the x-axis, skin depth decreases. The top two images represent cross-sections of the conductor, in our case, cross-sections of the antenna. At the lower frequency, the signal travels in the very center of the conductor. As the frequency increases, the signal starts to travel closer to the edges. And so now we understand that as the signal moves to the outer edges, the surface finish will also have an effect on that signal transfer. In this chart, we're looking at how surface finish, how it affects frequency and insertion loss. So on the x-axis, again, we have increase in frequency. On the y-axis, we have insertion loss in decibels per inch. The blue lines represent your bare copper control, immersion silver, and organic solderability preservative. The green line is immersion tin, and the red line is electroless nickel immersion gold. So we can see that as frequency increases, the role of the surface finish will actually affect the insertion loss. The finishes used at 24 gigahertz may have only experienced a low amount of loss, but as the frequency increases, the losses become greater. The most predominant surface finishes used for 77 gigahertz radar designs are our immersion silver process called sterling silver and our organic solderability preservative called NTEC Plus HT. Again, it's obvious that the previously preferred immersion tin for automotive is not functioning well at the high frequencies, and so designers must make changes. As the technology continues to advance, the systems will be required to have greater resolution, right? The cars must understand what's happening around it and be able to identify and refine what it is actually around the vehicle. To make advances in your technology, you will need advanced materials that match your expectations. We have over 60 years of experience in the electronics industry, serving all market segments. We specialize in the development of advanced materials, and we have a complete understanding of the expectations of the automotive market. We understand the focus on harsh environments. In our next discussion, we'll look at how heat affects product reliability. We'll specifically look at enhanced solder alloy to address current material shortcomings. I thank you so much for joining me, and I look forward to continuing this discussion with you.